We can start. I have a good news and a bad news. The good news is that this is the last talk of the day. The bad news is you have to sit through and chair us. Can we start? Thank you. Thank you. So my name is Senthil, and he's Akash. We build AI products at Rippling. How many of you heard Rippling? OK, reasonably popular. Imagine you're running a company. We have a few thousand employees across multiple countries. You have full-time, part-time, and contract employees, multiple departments, different access controls. You run payroll benefits, and you handle the payroll taxes. You manage their devices and all this stuff. And you are HR lead at a company. And on your Monday morning, your inbox, your CEO is asking a question. Hey, give me the report. And your CFO is asking some reports around spend. An employee, probably disgruntled, asking about like some missing amount in the payroll, and things like that. So you're filled with all these kind of requests. You know the answer is there somewhere across all the systems that you're managing and all the spreadsheets that you're handling it. But getting all these things done quickly and getting it accurate is just boring, and it's work. What if you could just ask your system, and it's going to give you the answer? Right? That's Rippling AI. So this is possible because the way we organize the system at Rippling from day one. Instead of multiple systems that you are dealing with, we put employee data at the center, and then we built a lot of products around it, and we call it employee graph. So you have all the systems connected. Whenever you change something with the employee, everything is reflected everywhere. And the data is already organized for you to use it. And we put a layer on top of it, and suddenly it feels like a magic. And that's what we did with Rippling AI. We launched like a few weeks ago. I've been with the company for like six and a half years now, and it's one of the most successful launches we've had. And that's possible because we have this data already organized with employee graph. So in this talk, we're going to talk about how the Rippling AI works and the journey, whatever we learned, and we thought we will be sharing this with you. And that's it. So let's talk about the architecture first. Whatever I spoke about employee graph, all this applications put together and the data, I'm representing that as one beautiful big block in the bottom called Rippling Backend API. And then I'm going to zoom into the agent itself. We use LangGraph, of course. And we have a top agent, and then we have a deep agent, which is handling the overall integration. The top agent handles the orchestration. There are three main blocks I'm talking about. First is entity resolution. If a user is asking, hey, what's the issue with Matt's payslip? The Matt has to be resolved to an employee, which is living in the system, pointing to an employee ID. And then we have tool selection, which is specific to the query. We need to select the tools, and we also need to bring the domain context, which is very vast in the case of Rippling, through skills and AOP. So that's a horizontal concern at the top. And then we have agent, which has some generic tools, and it also has, now that it has the entity, it has the tools, it has the domain context, it uses this, the agent runs it, and then it connects to the employee graph, brings the data, gives you the answers, operates the workflows. But we didn't start with this. When we started this project, Rippling is a few hundred member engineering company, and the products are vastly different. So we started with one top-level AI assistant agent, and then we had a lot of sub-agents, and each team can build their own sub-agent. That didn't work well. Primarily, the problem is around like how to do context sharing. How do you handle interrupts across the agents? Whether the top agent should know fully about the sub-agent context or not. How do you handle interrupts? How do you handle queries that are across multiple sub-agents? And then that became messy. So we just removed the problem by keeping it flat. What we have is one flat agent today, and all the domain context of different products are being injected into the agent only through declarative skills and AOPs. Our product teams, engineers write them, and of course, they test it. And the agent itself is like one flat agent. If you really think about it, like we actually removed a lot of abstractions in code. We kind of flatten in such a way that whatever a user sees as a message history, the same thing LLM sees, and the performance is much better with this. Moving on to the next topic. When we started, each team built their bunch of like tools, and we had like a big amount of catalog of tools. The problem with that is that like the tool selection became like has to be like far more sensitive. If we select wrong tools, if we miss some tools, that you're not getting the right answers. So we just like eliminated the problem by moving towards more generic tools. Here is an example. Instead of like a lot of get data, you have like one read data method, and then the employee or device or taxes becomes like a parameter. If you think a little bit about it, like it's same Unix philosophy that like do simple things and do it well, and let the agent compose all these things to get any complex outcome. Our AI assistant could do a lot of things. You can tell to run a payroll and hire an employee, and a lot of operations you can do. But primarily, people are using it to ask questions to get some data. It could be an individual asking about their payroll data, or like some of the benefits data, or some of any data that they're dealing with, or it could be the company admin or HR asking like even more aggregated data, report data. And this data cannot be wrong. And we all know that like stuffing the raw data to the LLM, that like, hey, this is the data, this is the query, answer this kind of prompt if we go ahead with, it can lead to hallucination, and we cannot afford to be wrong. So what we did is that like we specify LLM that this is the shape of the data, here is the data, and ask LLM to, here's the query, and ask LLM to solve that, and LLMs come up with SQLs to solve it. And we execute the SQL. So data itself is not part of the context scope. It's basically LLM solving the problem given the shape of the data. Interesting side effect of this, what we discovered is that like SQL is so powerful that we didn't have to do, it's far more powerful than building a lot of bespoke tools that we might have to build. I'll give an example. Consider a query, why weren't the benefits deductions withheld for an employee? Now, this looks like a very simple query. But underneath the system, we need to know about the employee, like the location, the entitlements, and everything. That's HRIS. We need to know about the benefits. Then, of course, it's payroll. So we need to just orchestrate across all these things. When you have like multiple tools, you can get this information and like kind of compose it. But we built like one generic tool to pull all the data with, and it can execute SQL. LLMs are really good with writing SQLs, and the moment we expose this context and expose the schema on the context, LLMs can write SQLs in one go and get the information it wants. And this was like far more powerful, and we kind of like reduced, and it also reduced the number of tools that is needed, which also removes the kind of tools going wrong and things like that. But this still has one problem. The problem is that like fetching this data, the data answers is like against all the core data lake. Getting this data is costly, both in terms of dollar and also in terms of the time. So what did we do? So what we did is that like we take this data once, we put it in a cache, and we let the LLM to say that, hey, this is the schema, this is the data, this is the query, explore and give us the answer. And you might have seen if you're working with Cloud Code or any of the agents, right? It iterates, it writes the query, figures out the problem, and then like if it is error, then it iterates and get the final answer. This is very helpful. We cache the data, and especially when you want to have the same data and have like 2 hypotheses running, and like the user is asking follow-up questions. It's very, very powerful, and this made the experience much, much better for the users. So far we've spoken about like what aspect of the system. We're going to kind of switch gears and talk about like how we kind of release the system, how we iterate and do. And that means we are going to talk about
Evals. So what we do at Rippling is, we say evals first and build next. So does that mean that, hey, you know what, you write your evals before you even have your agent running? No, that's not what I'm talking about. Let's say you have your agent running in production, or you have some version of agent running. Now, to make any meaningful change, you make your system prompt change, or you change your tools, your tool descriptions, your skills, anything, you don't know how it's going to behave, even if you know every single line of code, because you don't know how the LLMs are going to behave, right? So it's very important to say, hey, any meaningful, you can go by your intuitions. At the end of the day, the evals tell you the truth. So that's what we call eval-driven development, and we follow this extensively. So EDD, eval-driven development, is like TDD, the test-driven development, but harder, right? So given the stochasticity of the LLM in the first place, let's say you have an eval. You run it once, and it passes one time, right? So is the success rate 100%? Are you really sure? Let's say we run it a few more times just to be sure, right? So let's say you run it 3 times, and you've run it 3 out of 3 times, and it's successful. Is it 100%? Are you really sure? So there are some ways to figure out, like, how certain can you be as and when you get more repetitions in your evals. So you can't run it just once and say that, hey, declare victory, right? Because you run it a few more times, it might fail. There's some scientific ways. For example, if we were to plot, there's something called Wilson's confidence interval. So if we were to say that, hey, 1 out of 1 eval pass, at a 95% confidence interval, you could be as low as 20%. And at a 3 out of 3, you could still be, your lower bound could be 44%. And as you increase the number of reps, it's going to converge to your true pass rate, right? So the more the number of repetitions you have, the more confident you can be of your evals. And there's a scientific way of saying how many reps do you need for your evals, right? So the more repetitions you have, the more certain you can be. The less repetitions you have, the less certain you are, right? So repetitions reduce the amount of uncertainty you have in your evals. Now, so how many repetitions do you really need for your evals, right? So that needs 3 things. One is, where are you right now? What is your baseline, right? So let's say, for example, your eval is already at like 95%. Like the number of repetitions you need would be very different from if your eval is performing at like 85 or 75. The second thing is, how small a regression are you trying to detect? For you to detect something from 95 to 94, you need a lot more repetitions than for you to detect something from 95 to, let's say, 70%. The same way, it would be very different from if you were to detect something like 85 to like 60%, right? So, and the last thing is, what is your tolerance towards, a false positives over there? And so all of these things brings us to, you have cost, uncertainty, and lag, right? So cost is like, of course, the more the number of reps you have, the more money you're going to spend on your LLMs, right? And uncertainty is the more the number of reps you have, the less uncertain you are, or the more confident you are. And lag is how soon can you detect your regression from the time you've made the change. Let's say you've committed your PR. How quickly can you detect that, oh, there's been a regression on this? And you can only get 2 out of 3 over here, which means you can get low cost and low lag. At Rippling, what we do is we have something called as smoke evals, which are very few evals, and which we run for fewer repetitions, and we run on every commit that goes in, right? So that gives us some amount of confidence that nothing is majorly broken, but something could still be off, right? So what we do is that falls under the low cost and the low lag. And then what we do is, before it gets pushed into production, we have a pre-prod stage where we run something called as health evals, where we run it like twice a day, and we have many more evals running for many more repetitions, but we wait for a few bunch of commits to come in, which means that we're accepting higher lag, but we're reducing the uncertainty and the cost because we don't run it on every commit, right? So you can only get like 2 out of the 3, and then once health evals pass, they go into production, right? So once you have it in production, there are a few things that you need to keep in mind. Every domain, every agent is different, right? So no matter how many generic tools you have to have visibility into your data, so for which you need to build custom tooling, right? So to explore your data and to understand what is going wrong with your systems, right? So that is one thing. So you have to build custom tooling. The second thing is we have a vault workspace where all the production data goes in. We handle PII. And those things, we carefully kind of get us into the test environment, which is a synthetic test, which is representative of the customer data, but we don't work with the customer data, right? So we have a vault workspace, and we improve our eval suite over time based on the learnings from production. So finally wrapping up, first thing is keep your agents flat. And of course, this is going to change as models improve over time. Like last year, what you would have done is very different from what you're doing. Probably last month, what you would have done is very different from what you're doing right now. And what you're going to probably do 6 months from now or just next month would be very different. So as models get more and more powerful, the most important thing is to get your glue code out of your agents and let the LLM do its job, get out of its way. The next thing is, of course, build generic composable tools, which means that if you have data where you can let your model code, write SQL, let it do that. It's much more powerful in doing those. And when you get those things into the most fundamental atomic pieces, like your LLMs can do far more. Sorry. The next thing is, of course, eval first. Always ensure that you have your eval-driven development, and you test each one of your chains. No matter how good your intuition is, evals tell the truth. And you have to choose cost, uncertainty, or lag, right? 2 out of the 3. And thank you.